right, just a couple of housekeeping items before we move on in our discussion of IR. So first thing is if you go on Canvas, so on our class's Canvas page and look at chapter 14, okay, you'll see that I have the lecture notes, the suggested practice problems, the homework. And then the next thing says IR NMR tables Klein PDF. So I'm going to show you what that document looks like. I have it open right here. And this is a table that you will always have access to for your quizzes and yeah, just for the quizzes. You won't have it for the final, but you have it for the quizzes, okay? And this is what's going to be pertinent for us in chapter 14, okay? So whenever you hear me referring to a table, I'm always referring to this table, which gives you all of the IR absorption frequencies, which we're going to go over in some detail today. The second part of the table, that's for chapter 15. So this is for chapter 15. However, I leave it on here because later on we're going to need this part once we get to chapter 14. But again, I'm going to refer to this table a whole bunch of times when we're solving problems. And in fact, this morning we're going to take a look at a problem where we're going to compare alcohols and carboxylic acids, for example. Okay, so that's, you know, a couple of the easiest functional groups to recognize in organic chemistry. So somebody says, as far as the final goes, would it be helpful to memorize these? The idea is that these are kind of like, this table is kind of like training wheels, and that by the time you get to the final exam, you can rip the training wheels off and just cruise, okay? And, you know, the rationale there is that there's no tables given on the ACS, there's no tables given on an MCAT or a DAT or anything like that, okay? So we use it for the quizzes only, and then we don't have it for the final exam. Okay, so that's the first thing. The second thing is after that IR and NMR tables, then you'll see something that says IR practice Klein. And these are just some problems that I picked from the textbook. And we're going to take a look at some of these this morning. Okay, so we're going to take a look at some of these IR practice Klein. And then not this morning, but I'm going to ask my students to do this outside of class. Is if you look at our announcements, I posted an announcement this morning where I have an IR practice with guided solutions. So I provide a link to a playlist on my YouTube channel where I cover all of these practice problems. And they're also posted in the chapter 14 module, but I highly recommend that you go through the guided solutions. The reason why I made the video is because I've taught the class long enough to know that with so many different students that people kind of really do these things at a different pace. Some people are able to solve them pretty quickly. Other people take, you know, more of a methodical approach. And so that's why I made this. You can pause the video if you want and kind of go through the problems one by one that way. Okay, so a whole bunch of practice that I have available. And again, the reason why I've done this is because not only for different learning styles, but because practice makes perfect when it comes to IR. So let's get back into the concept of infrared spectroscopy. So just bear with me as I find the file here. And where we left off, we talked about wave number and we talked about how it relates to bond strength. That's kind of what we were looking at last. We were kind of here, right? We said if you have a conjugated ketone or a conjugated ester, the carbonyl is going to absorb at a lower wave number than if you have one that is not conjugated. And so the next characteristic that I'm going to look at is intensity. Now, again, our textbook goes into quite a bit of information about intensity, but I can make it much simpler than they do, okay, the whole intensity concept. The idea is that the intensity of the IR signals can vary, okay? So sometimes you get a really strong signal. And what that means, if this is transmittance, right, that means that if you have something that's down here, has a peak way down here, okay, that means that almost nothing went through. So what does that mean? If it has low transmittance, that means it has a high absorbance, okay? And then here, since this is mostly transmitted, that would mean it has a lower absorbance of the infrared light. So the stronger the signal, the more infrared light that was absorbed. And if you're wondering, well, why is it strong sometimes and weak other times? And then other times it's kind of in between the two. Great question, okay? And the answer is shown right here. It says when a bond undergoes a stretching vibration, the dipole moment oscillates, right? So let's imagine you have, let's say, a carbonyl like this, right? As you have the bond stretching, we know that there's a dipole in here. And so the dipole, right, this is the dipole moment. So if you don't remember, this is dipole moment, which is mu, okay? That's going to fluctuate. And it says that the oscillating dipole moment creates an electric field. And the more polar the bond, what happens is that the electric field created by the oscillating dipole moment acts as like an antenna for picking up the infrared radiation from the spectrometer. And so the 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 Sparks Notes version of it, and really what you need to know, is nothing more than this: the more polar a bond is, the stronger the IR signal is going to be. You see that we have a double bond here, and there's only a tiny, tiny, tiny dipole. There's a tiny, tiny difference in electronegativities between this carbon that has two hydrogens and this one that has two carbons attached. And so the dipole moment is really tiny. And so therefore it's going to have a weak absorbance, right? Weak absorbance for a weak dipole and a strong absorbance for a strong dipole. So, you know, a good organic chemist, he or he is going to look at a signal like this and say, well, that's got a strong dipole because it's a strong signal. Well, this signal might be pertinent, but it's weak, and therefore that means it's got a weak dipole. All right, so that's where intensity comes from. So here it has shown a really good example of a carbonyl that has an absorbance of maybe around 1710, 1720, something like that. Let me see, something like maybe 1720, okay? And then you have the carbon-carbon stretch here, which has an absorbance of around, I don't know, looks to me around 1650, something like that, okay? But the idea is that since the carbonyl is much more polar, it's going to have a much greater absorbance, or it's going to have less of a transmittance, right? Less of the light is actually going to go through the sample. The sample is going to absorb the infrared light. There you go. So let's move on from there, okay? Now, next it says if a bond is completely symmetrical, then you might not even see a stretching frequency, right? If you look at this compound, this is 2,3 dimethyl 2-butene is the name of this compound, which is neither here nor there. But you see that we do have a beautiful double bond in this compound. And so it's an alkene. If you go over to the table, so just bear with me as I go back to the table here. So here's our table, okay? And it says here that for an alkene, okay, for an alkene, where is it right here, that we should see a weak carbon-carbon stretch at around 1630, okay, something like that. So let's go back here. Let's go back to the slides. And if we look at 1630, so let me draw a line here with my ruler. So this is 1600, 1650. So maybe this is like 1630, something like that. So if I draw a line around here, and they're saying the expected signal would be around here, but either way, we see no signal in the spectrum. And so does that mean that we don't have an alkene? No, it just means that it's completely symmetrical. So there's no dipole moment whatsoever, okay? So that's why we don't see any signal. No dipole moment. And remember, in science, you can't prove something by a negative. You have to have a positive to prove something. All right, so let's move on from there. The last characteristic of a signal is its shape, okay? Some signals are broad, okay? Some of them are broad, and some of them are very narrow. Now, why would that be? Well, this is actually connected to bond strength, if you can believe it or not, okay? So things like an alcohol, for example, the oxygen-hydrogen stretching in an alcohol or a carboxylic acid usually gives you a very broad stretching frequency, okay? Very broad signal. And there's a good reason for that. And like I said, it's tied to bond strength, and it's also tied to the idea of hydrogen bonding. So let's take a look at that. So check this out. If you have an alcohol, right, this is just, this molecule here is actually ethanol, the alcohol that's found in alcoholic beverages. But anyhow, you see that you have ethanol here, and everybody who's hearing the sound of my voice should be able to show hydrogen bonding, right? This is a hydrogen bond, right, occurring between the hydrogen of one hydroxyl group and the lone pair on another. Well, the idea is this, is that hydrogen bonds are transient, right? They're intermolecular forces, but they're not nearly as strong as covalent bonds. And so since they're transient, what that means is that sometimes the hydrogen is going to be undergoing a really strong hydrogen bond, which is going to weaken it. And other times it might not be undergoing any kind of hydrogen bonding whatsoever, right? It's in between hydrogen bonds. So what does that mean? It means you're going to have a whole variation in bond strength. And didn't we say that wave number was directly proportional to the force constant or to bond strength? And so if we have variation in our bond strengths, that means we're going to have varying wave numbers as well. And so we end up with a signal that gets broadened, right? If we go back up here, this part of the signal is where it's going to be stronger, so where there's going to be less hydrogen bonding, and down here is going to be where it's weakened. But the idea is that we get a whole bunch of signals. The average is going to be down here somewhere. Give me a thumbs up if you follow me, partly on that idea of the hydrogen bond kind of stretches the bond back and forth. Sometimes it weakens it, sometimes it doesn't, and so you end up with a broad signal. Now, I'll be honest with you, I've never asked a student a question about, why does the hydrogen bonding blah, blah, blah. Basically, what you need to know as a chemistry 3101 student is that if you have a OH bond, hold on, everybody. I'm having a technical difficulty with my iPad. Just bear with me for a second here.